with few seconds of advance. So welcome everybody to the second black hole shadow session. So we will have 5 talks. So as I said before, it's 12-minute slot per talk. So the first talk will be given by Dipanjan Day, and he will speak about shadow of naked singularity. So Dipanjan, it's yours.
Okay, hi everyone. So can you hear me first? I'm clear? Yeah. Okay. So hi everyone. First, I would like to thank the organizers for giving me the opportunity to present our work here. So in my talk, I will explain what is the necessary condition for the existence of the shadow. And I will also show how a naked singularity can cast a shadow. So as we know, it was 10th of April 2019 when ngEHT group first released the image of the shadow of the compact object at the M87 galaxy center. It is a general belief that every galaxy hosts a supermassive black hole at its center, and therefore the shadow of the M87 galaxy center is considered as the shadow of the supermassive black hole. However, there are many recent works which show that the shadow is not only the property of a black hole, but it can also be cast by other compact objects like gravastar, naked singularities, boson stars, etc. Therefore, natural question arises: what are the necessary and sufficient conditions for a shadow formation? How does a shadow form? So, is it because of the existence of event horizon? Or is it because of the existence of photon sphere or something else? So in some of the recent papers, the necessary and sufficient condition for the existence of the shadow of a spherically symmetric compact object is investigated, where the authors show that shadows should form when there exists an upper bound of the effective potential of null geodesics. So this is the main condition for the shadow formation. So there are you can see that there can be different types of effective potentials. So these are the effective potential which can have the upper bound, and you can see the first effective potential. So it has a maxima, and that maxima is also the upper bound of the potential. Other two potential has upper bound, but they have no maxima. So for the potential which has a maxima, one can define a critical energy of photon, EC, with which photon can rotate multiple times on a surface of radius Rm, which is known as photon sphere. Photon with energy less than that critical energy less than that critical energy would be scattered by this effective potential, and photon with energy greater than that critical energy would be plunged into the central object. So in the right hand side, one can see the behavior of null geodesics corresponding to this potential. One can define a critical impact parameter. One can define a critical impact parameter corresponding to this critical energy of photon. Photons with impact parameter less than that critical impact parameter will be plunged into the central object, and photons with greater than that critical impact parameter will be scattered by the compact object. Therefore, from a circular area of radius BC, no light geodesic can reach to the asymptotic observer, which causes a shadow of radius BC. Shadow of radius BC with respect to the asymptotic observer. So I think there are some disturbances around.
I think it's settled now. Thank you, Lindy.
Okay, so for the potential which has an upper bound but does not have any maxima, one can also define a critical energy. One can also define a critical energy of photon, and corresponding to that critical energy, there exists a critical impact parameter, and for that reason, this type of potential also can cast shadow. Okay, so this first potential, as it has a maxima, and that maxima is also the upper bound of that potential, shadow and photon sphere both exist for this type of potential, and for these two potential, shadow exists but photon sphere does not exist, as there exists no maxima of this potential. There can be other type of potential where you can see this these two potential has no upper bound, but the left hand side potential has a local maxima. So these two potential also can exist in different compact object, and as they have no upper bound, shadow does not exist for these two cases. But for the left hand side, there exists a photon sphere. So though photon sphere exists, shadow does not exist for this case. But for this type of potential, effective potential, shadow and photon sphere both do not exist, because there exists no maxima, and also there exists no upper bound of that potential. So this potential which has a maxima, and that maxima is also the upper bound of that potential, can be present in different type of compact objects. First example is the short-scale black hole. This potential can be seen, this effective potential of null geodesic can be seen in this type of space-time, in this short-scale black hole space-time. And another possible scenario is if we consider a matter cloud, and outside that matter cloud, if we consider a vacuum exists, then one can construct a space-time structure which is internally a space-time which is seeded by some matter and which is matched with some external short-scale space-time. So here, for example, we consider Joshi-Malafarina-Narayan 1 space-time, which can be shown as an equilibrium configuration of from a gravitational collapse. This, if we consider this space-time as an internal space-time, and outside is the external short-scale, and if the matching radius of that space-time is less than 3m and greater than 2m, means it's greater than the event horizon radius and less than the photon sphere radius, then the lensing effect on the light-like geodesy would be same as one can see in the short-scale space-time, because the photon sphere is outside of the compact object. Another possibility is that a naked singularity spacetime itself has its potential like this, and for that reason it has a photon sphere. One of the example is the Janice-Newman-Winnicott naked singularity spacetime, which can cast shadow due to the existence of this type of potential for some suitable parameters value. Okay, so now I am going to show the shadow of this type of space-time, where you can see that these are the shadow which is simulated by considering by using the ray tracing method and considering spherical accreting matter which is emitting monochromatic light. So now you can see that the shadow of JMN1 and short-scale black hole space-time is almost similar, and here you can see the JNW space-time shadow is smaller than the shadow of the short-scale black hole. Now the potential which has only the upper bound but it has no maxima, this type of potential also can exist in different compact objects. Like one example is this null-like naked singularity, where m is the mass, ADM mass of this naked singularity. As this potential of null geodesy exists in this space-time, the space-time can cast shadow. And also this is true for time-like naked singularity. One can also derive this type of space-time from the two conditions. This is the one condition is the time-like singularity, and another condition that this potential should exist in this type of space-time. So this space-time also can cast shadow. So these are the simulated shadow of those space-time where the first shadow is for source-child black hole, and this shadow is for the null-like naked singularity, where you can see that the shadow size of the null-like naked singularity is 1/5 of the shadow of the black hole. But for the time-like case, the shadow size can be greater than and less than the shadow of the source-child black hole. So time-like singularity can cast shadow which can have radius greater than or less than the shadow size of the source-child black hole. So
Sorry,
so these are the important points what I am going to emphasize. So the main point what I discussed is that the shadow always should be there when there exists a effective potential which has an upper bound. And another important point here is that time-like and null-like naked singularities, shadow of time-like and null-like naked singularity can be observationally distinguishable, and it can be distinguished from the source-child black hole. So yeah, that's all. Thank you. If you have any question, please ask. Thank you.
Thank you very much. Are there questions for Dipanjan? So as usual, please raise hand in Zoom. So if not, I have one actually. So do you consider computing maybe a more astrophysically realistic model by considering some kind of accretion flow around your compact objects or not?
Yeah, means thin accretion disks. Our collaborator considered that thin accretion disks around naked singularity. Thin accretion, optically thin.
Because
it is also similar to the black hole case for some cases, and also for some cases it can be distinguishable.
Yeah, because I guess the fate of matter is different than black hole because you don't have the event horizon. So do you know what
it can have? It can have innermost circular orbit up to Earth tends to 0. So for black hole case, the innermost circular orbit, there exists innermost circular orbit. So.
Okay. Thank you, Dipanjan. I think we have to move to the next speaker. So the next speaker is Francisco Duque. If you can share your screen, Francisco.
Can you hear me well first?
Yes, we can
Awesome.
hear you. So Francisco will tell us about the light ring and the appearance of matter accreted by black holes. So you have 12 minutes, question included.
You can see my screen, right?
Yes.
Awesome. May I start?
Yeah, please go ahead.
So, good afternoon, everyone. I'm Francisco. I'm a second-year PhD student in Lisbon, working under the supervision of Professor Vitor Cardoso. And I'm here to tell you about the recent project we worked on, in collaboration also with Ariana Foki, and which concerns the universal properties of how matter being accreted by a black hole appears to us, and the impact of this on the science of black hole imaging. And before we jump into our actual problem, let me just give you some quick motivation to study it. So using telescopes, we have been observing several periodic high-intensity flares coming from the center of different galaxies. And we do not know for certain what causes them because the physics involved here is extremely complex, but we think with a certain level of confidence that they are related with the accretion of matter by the black hole that is present in the center of these galaxies. For example, recently, the Gravity Collaboration reported near-infrared flares, which they think originates due to strong lensing of light that is being emitted by a source that is very close to the horizon of Sagittarius A star. And whatever the real reason behind these flares is, they certainly occur in regions of space-time where gravity is very strong and essentially determined by the central compact object. But we know from our own experience that high-frequency processes that generate a significant portion of energy near a black hole tend to be very efficient at probing the strong field properties of the gravitational field. And the best example that we have of this is perhaps black hole binary systems, in particular, the last stage of a binary black hole coalescence, which is called the ring down. And in this stage, the signal is well described by a superposition of exponentially damped sinusoidals, where these characteristic frequencies are related with the relaxation timescale of the final compact object. Then this allows us to do what is called black hole spectroscopy, where we measure these frequencies and compare them with the values predicted by the theory. And since for a particular theory of gravity, they only depend on the internal properties of the final compact object, like its mass and its spin, we can test the nature of black holes and see if they are really described by the Kerr geometry or if they are something else. But as we have heard today, the ring down can also be understood in terms of marginally trapped waves at the light ring, which, as we have repeatedly heard throughout this week, is the region of spacetime where massless particles can be in unstable closed geodesics. And for a non-rotating black hole, this region defines a photon sphere with these properties here. Then the ring down corresponds to the leakage of these marginally trapped waves as they escape to infinity. And it is the time scale associated with this escape, so how fast it is happening, that determines the frequencies that we measure. So our question here was if there was an analogous ring down, but for the accretion of luminous matter by a black hole. And this problem was more or less studied many, many years ago, first by Zeldovich and then complemented by Amts and Thorne, but in the context of spherically symmetric collapse. But here we want to investigate what happens close to the light ring, so even inside it. So a body that is emitting any types of waves fades out as it is accreted by a black hole, because as we saw in the case of the flares, we might be able to observe these kind of processes. And we started by doing this in the geometric topics limit, where we put a body falling radially onto a black hole and make that body shoot photons at proper constant energy in its rest frame. And we studied this for two different bodies. The first one is a beam that only shoots photons radially outwards, so they are always able to escape to infinity. And what we see is that distant observers measure photons that are progressively redshifted, as we would expect, and this redshift happens due to Doppler effect and due to gravitational redshift. And at late times, after the source has crossed the light ring, the redshift follows an exponential decay, which leads to a decay in the luminosity of the source, which is given by this expression here. But perhaps more interesting is what happens in the case of an isotropic emitter, for example, a star, that is shooting photons equally in all directions in its rest frame. And in this situation, distant observers measure a wide range of redshifts. The photons which are more redshifted are those that follow the same paths as in the case of the beam, so radially outwards. But we also see that some photons can actually be blue shifted, and these are a consequence of extreme bending near the light ring, where light rays which have a near critical impact per meter can circle the black hole and be reflected back to infinity. And as a consequence of this blue shift, the late time behavior of the luminosity now follows a slower exponential decay, whose frequency is controlled by the frequency in which these photons can be in circular motion at the light ring. So this is the first hint that we have that indeed this structure plays a role in how we see accretion. But actually, we had observed a similar behavior as this in a previous work of ours, but in the context of hierarchical triple systems, where we have a stellar mass binary system orbiting a supermassive black hole. And to test how generic this apparently decay was, we now, instead of looking at null geodesics, look at waves propagating in the background spacetime of non-rotating black holes. And to do this, we use Stokowski's equation, which is a second-order wave equation that describes general perturbations to the Kerr spacetime. And the inhomogeneous part will be our infall emitter, which is again vibrating at proper constant frequency in its rest frame. And what we see is that even though now the radiation has a wavelength which is comparable to the size of the black hole, the late time behavior of the luminosity still follows the same exponential decay dictated by the light ring frequency. And the differences you see here between the scalar case and the gravitational case, which correspond respectively to spin weight 0 and spin weight -2, are due to the differences in the source terms that we took. And in particular, for the gravitational case, we considered a binary system, so there will be low frequency contributions to the signal, which come from the plunge of the center of mass. But again, this is even further evidence of how generic this exponential decay is. And this behavior is also observed in the case of the energy flux that is measured by distant observers at different locations. Again, all these lines follow a global exponential decay that is even by the light frequency, but now you see that it's very clear that there is a high frequency content in the spectrum, and this high frequency content corresponds to blue shifted waves, whose blue shift agrees with what we saw in the case of the geometric optics limit. And what's happening here is that as a source falls onto the black hole, it feeds the light ring with energy, which is stored here. So the light ring basically heats up. Then as the source crosses the light ring, this transfer of energy is maximum. And then finally, as the source is approaching the horizon and it gets progressively redshifted, the energy that was stored starts to escape and the light ring starts to cool off. So this sort of thermodynamical interpretation of this process explains why these structures here have a periodicity that is always related with the light ring frequency. So by now, I hope to have convinced you that it is indeed the light ring that controls how dynamical processes happening close to the horizon look to outside observers. But remember that one of our motivations was to test the nature of compact objects. So now we are interested in understanding how our results change if we change the near horizon physics. And to do this, we studied two different processes. In the first, we turn off the source when this is located very close to the light ring. And as you can see in this plot here, there are basically no significant changes in the spectrum apart some mild variation in amplitude. And curiously, this is also verified in the opposite case where we increase the luminosity of the source close to the light ring. Even though now, if this increase happens before the source crosses the light ring, the change in amplitude can be much more significant. But again, the global late time decay is still given by the light ring frequency. So this result teaches us that two different compact objects which have a similar light ring might be hard to distinguish even if one of them has an horizon and the other has not, which sort of corroborates what Paolo Pani explained earlier. And my final punchline is precisely the statement that I've been repeating throughout my presentation, that the late time appearance of infolium matter is completely controlled by the light ring frequency. So our science case proposal is to do something similar as we do in black hole spectroscopy, but using measurements from redshift and luminosity, because different compact objects, which have different properties like a different mass and a different spin, will have a different light ring structure. And as we saw with all the results that I showed you, this will translate into different redshifts and luminosity. And this will allow us to test the nature of compact objects from these measurements. Thank you very much for your attention. And this is all I have to say to you.
Thank you very much, Francisco. Questions, Alex?
Yes, thank you for the nice talk. I think this point that if something falls into a black hole, the last radiation you get comes from the light ring is a very nice point. I've been looking at your paper, and actually just a technical point, there's something that confuses me a little bit. Can you go to the early plot of redshift from the infalling isotropic star as a function of time? Can you explain what the solid red is? Because it's a point source, right? So at a given point in time, you're getting discretely many images of the star, no?
Oh, okay, but
here, is the red curve filling does that mean that you get light rays of all those redshifts?
So this plot here is what the distant observers located in all the sphere at distance.
I see. So going vertically through the red region is changing the observer inclination.
Yeah, but actually I was expecting someone to ask that, so I can prepare. And this is what a single observer sees.
Yeah, it says in the caption to the paper that you had insufficient resolution.
Yeah, at late times we are not shooting enough photons because this takes. Sorry.
Why can't you shoot more?
Because it takes a lot of time. because as the source gets closer to the light ring, the photons will take more coordinate time. So our code, which is a very rudimentary code.
But it's not exponentially more time. It's just constant time. It's 16 m, right, for each additional half orbit. You don't need exponentially large time. You need.
Alex, maybe if you want to go into more technical detail.
Okay, sorry. Yeah, it's very interesting. Thank you.
Thank you very much. Thank you, Francisco. And I think we can move on to the next talk. So the next talk is by Rahul Kumar. If you can share your screen, Rahul. Okay, perfect. Thank you. So Rahul will tell us about testing rotating regular spacetimes with shadow observation.
Okay, so I hope I am audible to everyone. Okay.
We don't hear you.
Hello.
Yes, you are unmuted, but we don't hear you. Well, at least I don't hear you.
I guess, am I audible now?
Yeah, well.
Okay.
Okay. It's reasonably okay. You can go on, and Alex, maybe you are still raising your hand.
Yeah, Rahul, you're very quiet.
Actually, maybe there's a network issue. So, is it audible now?
Well, it's quite difficult to hear. Am I the only one for whom it's difficult?
Okay. So just give me a second. So,
for me, it's also difficult.
Okay.
It's very quiet.
If you speak very close to the microphone and very loud, it should be okay.
Yeah, sure. Just
okay. Now it's good.
Use VLBI for communication.
is it audible now?
Yes, let's move on. Just try to speak as close as you can to the microphone and
Okay.
loudly.
Sorry for the interruption. So actually, the scope of the present talk is to discuss about the viabilities of rotating regular black holes in space-time as astrophysical black hole candidates. And because most of the current understanding of our black hole physics depends upon the assumption that astrophysical black holes are described by the black hole solutions of Einstein field equations. But there are several modified theories of gravities which also admit non-curve type of black hole solutions, and they differ significantly from the curve black hole solution, especially in the strong field limits. And because the side observations offer one such potential tool to test these non-curve black holes against the curve black holes. So then one can actually test these rotating regular space-time with the side observations. And here is a brief outline of my talk. First, I will be discussing about the very interesting kind of black holes. These are the regular black holes, which do not have any curvature singularity at their center, and they have a finite upper bound curvature scalar. And then I will move on to discuss about the black hole shadow and testing rotating regular black holes, and followed by the summary of my work. So one important class of regular black holes are basically sourced by the nonlinear electrodynamics field. And if we consider a minimally coupled suitable Lagrangian density for nonlinear electrodynamics fields, then one can solve the field equation, and we get the regular black hole solutions. So for this particular type of Lagrangian density, we can basically
We have lost the sound now, Rahul. Do you hear me?
Yeah. So
okay, now we hear you.
Okay. Yeah. So sorry for the interrupt. Okay. So if we consider this kind of particular choice of Lagrangian density, then one can solve the field equation and we get the regular black holes. And so Bardeen and Hayward are the two first type of these regular black holes, and they have a de Sitter core at the center, but in the asymptotic large arc limit, they do not reproduce the region of some kind of black holes, which is basically solution of Einstein field equation coupled with the Maxwell linear electrodynamics. But if we consider the exponential form of Lagrangian density, then we get another type of regular black holes, which have a Minkowski flat core at the center, but they produce the region or some black hole in the weak field limit. So the rotating regular black hole metric can be written in the Kerr-like form. And because these metric have a sufficient number of isometries and the hidden symmetries, then one can easily solve the Hamilton-Jacobi equation, and we can get the equation of motion in the first order differential form. And then we can define the number few impact parameter to characterize the photon orbits, and depending upon their values of impact parameter, we can characterize the different type of orbits. So the input, we are only interested in kind of spherical photon orbits which moves on a constant radius around the black holes. And if we solve the radial equation, then we can get the critical values of impact parameter for impact parameter basically define spherical photon orbits around the black hole. And these orbits basically construct a photon region around a black hole, and shadow is eventually the lensed image of the photon region or the event region of the black hole. And then we can basically describe the celestial coordinate of the black hole shadow in terms of this critical impact parameter. And when we make a stereographic projection from the celestial coordinate to the observer screen, then we can define the Cartesian coordinate of the black hole shadow boundary. So we know that in the modified theories of modified theories, the rotating black holes they have a slightly non-circular shadow, and to describe the size and the shape of black hole shadow, we define three shadow observables: area, circumference, and oblateness. These they can be defined purely in terms of the black hole shadow boundary, and they are completely independent of the accretion and emission process, because ultimately it will not it will not alter the black hole shadow boundary. So now actually we consider that if we are given by a black hole shadow observables, then we estimate the values of black hole parameter for Kerr-Newman, Bardeen, and non-singular, and we find over here that a given shadow can infer a various type of black hole models. However, the values of black hole parameter can be precise, it can be differ. If we see carefully, the spin values of for Kerr-Newman black hole is different from the that is extracted for the Bardeen and non-singular black holes. However, it is also possible that a given shadow can correspond to a unique black hole. But the point is that a black hole shadow may not correspond to a unique black hole. So now we actually test these rotating regular black holes shadows with the Kerr black hole, and for this purpose we consider the Kerr black hole shadow as injection to test fit with the rotating regular black holes model shadows. So for this we consider shadow area and oblateness as observables. Alpha and sigma is the uncertainty in the current observations by EHT. And we calculate the chi-square, and basically we try to see if a given Kerr black hole shadow can be explained with these rotating regular black holes. And if we see over here that chi-square is less than 1 for a finite parameter space, it means that a given rotating regular black hole can explain a given Kerr black hole shadow. And we calculate this chi-square for different values of Kerr black hole spin, and we see that even for the rapidly rotating black holes, there is a finite parameter space for which chi-square is less than 1. And in this parameter space, the rotating regular black holes can actually reproduce the rotating regular black holes can reproduce the Kerr black hole shadow. And we do the same analysis for Hayward and non-singular black holes, and the trend is same, but there is always a finite parameter space that for which rotating non-singular black holes can also explain the Kerr black hole. So now we test these rotating regular black hole shadows with the M87 shadow observables, M87 shadow that is captured by the EHT. So for this purpose, we consider two shadow observables, the circular asymmetry and the angular diameter, and we try to place the constraint on the rotating regular black hole parameter for which the shadow satisfy these observational bound. And we see that the angular diameter within 1 sigma region basically places stronger bounds on the black hole parameters. Now, actually, we moved on to the no-region spacetime, as Dipanjan already presented very beautiful analysis for the naked spherically symmetric, non-rotating naked singularities that they also mimic a black hole shadow. Here we present a rotating no-region spacetime for the, and we here show for the first of its kind that even in the no-region case, these rotating regular space-time for finite values, for some particular values of parameter, they can construct a closed photon ring, because we know that in the Kerr naked singularity, the photon ring is always open, and it is closed only in the case of Kerr black hole. So the structure of photon ring basically can give some inference of the cosmic censorship conjecture also. But we have shown over here that it is not true in the case of rotating regular space-times, because the photon ring can be closed even for the no-horizon space-times also. So, and here we calculate the parameter space for which the no horizon rotating regular space-time can have a closed photon ring, and we see that for the Bardeen, Hibbert, and the non-singular, there is always a finite parameter space. And then we calculate the asymmetric parameter for these closed photon ring in the no horizon space-times, and they then compare it with the M87 observables, and we find that there is a parameter space over which the circular asymmetry for these no horizon space-time photon rings can satisfy the M87 constraint. So in summary, we have seen that the rotating regular black hole shadows are basically smaller and more distorted than the Kerr black holes. However, it is also possible that a given black hole can correspond to various black holes. A given black hole shadow can correspond to various black hole models, and the parameters of these black holes can vary. And it is also possible, we have shown that a rotating regular black hole can explain the Kerr black hole shadow observables also. And the extracted values of spin parameter for these model shadows are basically different or biased from the Kerr black hole spin, and its biasness increase with the deviation parameter G. We place the constraint on rotating regular black hole parameter using the M87 set of observables, and we have shown that in the no horizon space-time, these rotating regular space-time can also construct a closed photon ring, and this is like in the contrary to the Kerr-naked singularity case. So thank you.
Thank you very much, Rahul. We have time for a very short question. So if there is no very short question, actually, I would have a rather technical comment for you, but maybe I will send you by email, because I think you are using the Bambi and Modesto rotating Hayward solution, right?
Pardon?
The rotating Hayward solution that you are using, is that it's a reference?
Yes.
Okay. So because this space-time is actually non-geodesic complete, and we have studied this in my group recently, but I will send you an email because it's a bit technical. Maybe
Okay,
it can
sure.
have interest for you.
Sure.
Thank
Okay.
you very much, Rahul. And we have to
Thanks.
go to the next speaker now, who is Marshall Eubanks, who will tell us about rings anchored in shadows. So Marshall, you have 12 minutes. I will tell you at 10 minutes that you have only 2 minutes left.
Can you hear me now?
Yes, we hear you. We don't see the slide.
Good. Yes, I have to share it. Sorry, I'm muting myself. Can you see the slides now? They should be coming up.
Yes.
Okay, so I'm actually talking about something a little different, and you might even say it's the ngEHT, but I'm talking about the let's see, let me put this in full screen here. Well, really the dawn of astrometric cosmology and how the ngEHT and its successor should be used in the future of the event of the celestial reference frame. If you use GPS or a cell phone, or for that matter, if you're flying a plane, or if you're on a commercial flight, or if you're trying to land something on Mars, you're using a VLBI-derived product, the International Celestial Reference Frame, and the things that are associated with it, like the UT1 data that the VLBI acquires. And that's actually paid for a lot of the EHT. I mean, I hate to be crass about these things, but, you know, there it is. And the ICRF is currently entirely defined by terrestrial VLBI observations, mostly between S-band and Ka band, in fact, entirely between S-band and Ka band. The most recent ICRF3 has goes up to Ka band. It's unlike what some people might have thought 10 years ago, plus it's not going to be replaced by Gaia. Gaia has its own issues about where the centroids of the radio sources are, the quasars. I'm just going to call them quasars. Of course, they're active galactic nuclei and a whole bunch of things, but you know, for our standpoint, just quasars I think is good enough. Standard picture, which you should have seen already. Right now, everything is limited on the ground by the frequencies used and by the atmosphere. And Broderick's paper actually goes into this very well, I think, for Sagittarius A star M87. So if you're, you know, so want to EHT perspective on it. You can go to that paper. And the limits right now are, well, the galactic aberration has been detected. I started looking for that back in the 90s. It was very marginal back then. Now it seems fairly firm, but there's still a sort of 30%, 20% uncertainty on it. And that's a few micro arcseconds a year. All right. So that's something like 4.85 micro arcseconds a year. I think that the theoretical model is 4.8. It agrees very well with what you'd expect, theoretically. It's due to the circular motion of the solar system around the galaxy. And so it's really the first sign in VLBI that, you know, of what's going on at the solar system, not just that the quasars might have jets and stuff, but the solar system is involved in the universe, you might say. And that means, by the way, and I think a lot of people don't appreciate this yet, that the celestial reference frame, starting with ICR3, is going to be of date, In other words, the positions of the quasars at the micro arcsecond level will change depending on what day it is. So the ICRF3, I believe, is for J2000. If you want to get the positions now, they're going to be 30, 40 micro arcseconds different. So really, though, they're if you get outside the galaxy in an isotropically expanding Hubble flow type, lambda CDM, Lemaitre, Friedman, Robinson, Walker metric type expanding universe, all transverse motions are peculiar. In other words, they are because of things going on that are not part of the cosmological expansion, per se. The cosmological expansion might be asymmetric, that's another matter, but it's not in the model. So what might you have? Well, there's an aberration or the acceleration of the solar system. This is so-called secular parallax. The cosmic microwave background data show we have a dipole that's corresponding to a 600 kilometers per second motion of this whole galaxy relative to the cosmic microwave background. We don't really know the extent of that, but even if it's very widespread, because of the acceleration and because of the expansion of the universe, that will change with time, and that change is about 78 micro arcseconds per year per megaparsec. So that's something we should be able to start pulling out soon. The gravitational waves, Carl Gwynn and I did a paper on this back in '97 with some other people. VLBI provides the only bound on gravitational waves between basically what pulsar timing can do and what the cosmic microwave background can do. And a very interesting one, which has just come up in the last 10 years or so, is the baryon acoustic oscillations. Those will cause changes at the micro arcsecond level, micro arcsecond year level, in the sort of the regional positions of quasars. BAOs have impose a standard ruler in the oscillations, and that standard ruler is about I believe it's about 15 to 20 degrees on a z of a half. So it's 5 degrees on a z and a half. And so that should be noticeable. We should be able to find that. All right. Why am I here? Well, because I feel like the ultimate goal here is going to be to anchor the ICRF in the black hole event horizons themselves, except of course the event horizons are a shadow. And so you can't really anchor it in the shadow. You have to anchor it in the photon rings or something like the photon rings, okay? And for this purpose, I don't really care that much how big they are. I know a lot of the discussions about what's the size, because that tells you about sort of like the gravitational model and so forth. It's really the centroid of it, and how well can you define that? And obviously there are effects going on, the Brownian motion, because of stars, moving around near the supermassive black holes. The so-called last parsec problem is part of that. But I think the photon rings are going to be what defines things in the future. So you've probably seen a view graph very much like this. It's the size of the photon ring, just based on that model on the last one, is a function of redshift. And you see the EHT there, a nice blob. The Sagittarius A star, of course, is not far off to the left there, and it's kind of small. But with an Earth-Moon VLBI network, we should be able to do this out to about a micro arcsecond, and so we should be able to get largest but not incredibly large event horizons all the way out to the observable universe, redshift of up to 10. Now, of course, faintness is another question. And so just,
sorry, just
2 minutes?
3 minutes to go.
Okay, just as an example, the kinematic proper motions. So you're talking about somewhere between 300 kilometers a second, which is sort of a typical galactic motion, to 6,000 kilometers per second. If your black hole's been ejected in a kick, that's pretty extreme, but not unheard of, I think. So, you know, you should be able to see those with Earth-Moon VLBI out to a substantial fraction of a redshift of 1, or maybe more if you have extreme kicks. So how do you achieve this? I think you have to go into space. And I think you have to start thinking about multi-beam systems. And I think you have to start, this is the Vera multi-beam system here. It's a very cool design with one antenna and multiple feeds. And so you can look at more than one object at the same time. However, that's not enough. And I was glad to hear yesterday some discussion of nodding on the ngEHT. That's been used with Vigos a lot. And that's also multiple antennas at one site are used a lot. So, and I think you're going to need both of those things to sort of densify this. And I think it'll require going to space. So this is not something that's going to happen maybe even by 2030. Probably won't. But I think it's a reasonable goal to have, as a long-term goal, to have the ICRF anchored on these event horizons. And as I said at the beginning, it's worth remembering that that's a source of revenue for the VLBI and for EHT. And looks like I could go into that. I have something on the Lunar Gateway, but I don't want to talk about that. So that's it. And if any questions, you know, I'm here.
Thank you, Marshall.
That should be about 2 minutes, right?
Yeah, we still have 2 minutes for questions. Yes, Gopal. Gopal, do you want to ask a question? Yes, please.
Gopal, you're muted.
Oh, I'm sorry. Nice talk, Marshall. Fascinating topic. I just wanted to touch upon one of your last slides where you talked about multi-beam receivers. What is the reason for pointing on 2 different positions while doing VLBI, or is this?
Oh, all right. Well, so this is a sort of commonplace in astrometric geodetic VLBI. The Broderick paper was mentioned yesterday. Actually does a good job on this, but it's kind of EHT focused. But basically, if you point at one source, it doesn't matter what the source is, and then you move to another source, you have the degradation caused because of the clock change in that time, the degradation caused because of the atmosphere change in that time, and at the millimeter VLBI level, the atmospheric coherence time is seconds. And so you basically can't nod fast enough to really stay in the same coherence patch. It's like twinkling of stars. You know, the stars twinkle incoherent. It's very much like that in millimeter wave. And not quite as bad, but you know. And so basically you need some way of getting from one star to another, or one source to another very quickly. And the way to do that is either you have multiple antennas and one antenna looks at one source, looks at another, or you have very fast beam switching, which is what Vigos tried to do. And so they have 3 degrees per second antennas, which means they're small, or you have multiple beams, which is what the Vera project did, and there have been some others like this. And this actually works really well. And that's movable, by the way, that one of those, you could say the red one is movable, you know, so one's fixed and one's movable. So they can actually slew over to 2 degrees or so and stay in the same beam and do everything simultaneously. And they've been doing really good work on parallaxes of masers and stuff like that with that.
Okay, well, thank you.
Okay.
Thank you.
You're welcome. Thank you.
I think we have to go to the last talk of the session. Thank you very much, Marshall. So now the next speaker is Tomohisa.
I'm going to mute now. Okay, thank you. Take care.
Bye. Tomohisa, can you share your screen, please? Who will tell us of possible appearance of M87 jet bases, with future EHT observation.
Okay, can you see my screen?
Yes, we see and we hear. Thank you.
Okay. Hi, everyone. I'm Tomohisa Kawashima from ICRR, University of Tokyo. And thank you for giving a chance to speak in this meeting. And today I'll be talking about our recent work on the possible appearance of the MET7 jet bases with the future EHT observations. This is a work that is recently accepted for the publication in APJ, and arXiv number is here. Okay, I will start my talk with a brief introduction of our motivation. Our motivation is the jet basis emission important for the ring images. So this this figure shows a set of observation images of MET7, and from left to right, the observing photon frequencies increases. And the left one shows the global jet images of MET7, and this one is a magnified view of the region here. And because of the higher frequency, the resolution increases, and the degrees of the cross-section for synchrotron self-absorption, the plasma becomes more transparent compared with the left one. And so we can see the deep region goes to the black hole from left to right. And finally, we can see a black hole shadow with a ring feature that is observed by EHT 2017 campaign. And we explore the contribution of jet basis emission to these images at 230 gigahertz in this work. Okay, so next I will explain the overview of the model setup. So based on some previous works, for example, Brodik and Tchaikovsky 2015, they proposed a model which the plasma is injected near the stagnation surface inside the jet funnel based on the spark gap model. So here the a figure which shows the location of the plasma injection in our model, and here the black hole, and this gray line shows the outermost stream line in the jet funnel, and the stagnation surface which separates the jet funnel jet with the how to say, the velocity of the radial velocity of the plasma equals 0, and in this region the velocity of the plasma is positive, and I mean that's outward direction the jet propagates, and in this region the jet moves inward due to the strong gravity of the black hole. And based on some theory, it how to say, the plasma will likely to be injected at the region where the magnetic field is stronger. And then the bottom of the stagnation surface is likely to be the plasma more likely to be injected in this region. So we simply assume that the plasma is injected at the bottom of the stagnation, and we call this the stagnation ring. And from left to right, the photon spin of the black hole increases, and so the photon shell, that is a bunch of the photon spheres of that is a bunch of the unstable circular orbit of the photon exists like this one, and then this region is enlarged due to the strong black hole spin. And at equal 0.99, then the stagnation ring overlap with the photon shell. And this is the important feature of the highly spinning black hole cases. And we solve the radiative transfer equation, and assuming the synchrotron emission absorption by non-thermal electron using GRRT code, our GRRT code RICO. And here is the important parameter set, how to say, table, and we set the number density of the plasma to reproduce the radiative flux 0.6 Jansky at 230 gigahertz. And in our model, the rotation velocity is assumed to be consistent with the GRMT simulation by Nakamura et al. 2018. and the resulting speed, how to say, angular velocity is almost 0.5 of the angular velocity of the black hole, half of the angular velocity of the black hole. That is consistent with some other previous works. Okay, let's move on to the result of our calculations in the next slide. Okay, here's the result of our calculation, and from left to right, and the black hole speed increases. The top panel shows the full calculation model, including both of the approaching jet and counter jet region. And the middle panel shows the result with only assuming the approaching jet emission. And the bottom panel shows the result with assuming counter jet emission only. So this inner ring is due to the emission from the approaching jet, and this larger ring is due to the emission from the counter jet. The counter jet ring is larger than the approaching jet ring because of the gravitational lensing effect, and the resultant image becomes enlarged due to the strong gravity of the black hole. And we can see the photon ring inside the counter jet ring, direct image of the counter jet. And because the photon ring size does not change significantly when we increase the spin of the black hole, and then but the counter jet images becomes smaller because the stagnation ring appears close to the black hole when we increase the spin of the black hole. So the two images almost emerges at the spin of the black hole is 0.99 because part of the stagnation ring overlap with the region of the photon shell. So we can see the almost 40 microarcsecond diameter image of the ring as is shown in the observation of EHT 2017 campaign. But it is important to note that we can still see some approaching jet ring inside the 40 microarcsecond ring images. So this might be inconsistent with the observed image at 30 gigahertz by EHT. So we examine synthetic observation assuming the EHT arrays in the next slide. So here's a synthetic image of jet emission model assuming EHT 2017 array by using SMIII by Akiyama-san. And here the top panel shows our theoretical model images, and the bottom panel shows the images using synthetic images assuming the EHT 2070 array. So for the model with lower black hole spin, then we can clearly see some double ring features, and the diameter is significantly larger than that of the observed ring images. So we can exclude these models. But for the 0.99, black hole spin 0.99, then the inner ring feature disappears because of the limited resolution of the 2017 array. And we can see the similar feature of the images observed by EHT 2017 campaign.
Sorry, sorry, to let you know you have 2 minutes more.
Sorry?
You have 2 minutes left.
2 minutes. Okay, thank you. So we can see the brighter region in the south region because of the Doppler, how to say, relativistic Doppler effect due to the rotation of the plasma. Okay, and so this means that the observed images will be important, how to say, may contain some important information of the jet biases in M87. Next, we consider the synthetic images assuming a forthcoming EHT array. The left one is a theoretical model, and this one is synthetic images for EHT 2017, as is shown in the previous slide. And this one is the images assuming EHT 20, 20, 21. And we can see a brighter spot inside the 40 microarcsecond ring. And for a more update of the EHT, then the EHT 2023 array will indicate the clear feature of the double ring, which was shown in the theoretical model. So we can examine our model using a forthcoming EHT. And let us briefly discuss about some relation to EHT 2019 paper. Here is the emission images of GR emission simulation for same model with black hole spin equal, sorry, here the higher black hole spin cases, and we can see the similar feature of the 40 microsecond ring plus inner region ring, inner ring. And of course, these tests passed the image scoring in paper 5, and because the same reason, possibly the same reason with us, our model. And so it will be reasonable that our synthetic images are consistent with observatory images. We know that our model involves the case of the emission from the highly magnetized panel of the MAD model. And so another model also indicates the multiple ring. For example, Vincent 2021 proposed emission model around the wormhole, which shows the multiple ring feature in the images. And also Rahul plus 2020 also demonstrates that the forthcoming EHT will enable us to study the emission near the jet bases, which can identify the different electron distribution models. And so future EHT observation will crucially important for the study of the plasma near the jet bases. And here is our summary, and I will stop my talk here. Thank you very much.
Thank you, Tomohisa. So we have one question for Andre.
Yes, a quick one. On your progression of images for different EHT configuration, I'm a bit surprised that you have an image in 2021 that shows a bright peak in the middle, although the weaker configuration 2017 shows that essentially what it should show in this respect. And then you go to 2023 and you start seeing the ring again. So there must be some funny thing going on with this imaging. That's very difficult to imagine that to improve the UV coverage, and actually this image in 2021 is the worst of all three. It means that you have some biasing, some aliasing towards the center out of some problematic, and it could not be a problematic with the UV coverage, because then you improve the UV coverage, you reduce the quality of the image, the fidelity of the image, and then you do the next stage of improvement, and it comes back. So I would check that. Over.
Excuse me. So the you mean that?
I'm surprised because again you have base UV coverage in 2017. Then you say you've get some additional improvement in 2021, and then the next stage of improvement 2023. But the fidelity of the image of 2021 is much worse than either the left or the right image, because that peak in the center, if it results from the true model that's shown on the left hand side, indicates some serious problems with the with reconstruction. And then I don't know from where these problems are coming, but I would really check that particular procedure, because
But again, I guess that the blob we see in the 2021 reconstruction is due to the upper left corner of the smaller ring that starts to appear, right?
I don't know.
Yes, this is a part of the inner ring.
I don't know why exactly it appears like that, but it's reasonable that there is some light here, right, in the reconstructed image.
It is maybe reasonable, maybe not. But again, that you do not see then the rest of the ring that does not appear anywhere in reconstruction, not even in sort of in broadening of southern rim of the main ring or anything else. You don't see any evidence for the rest of the ring. So well, I'm just surprised. Of course, I just looked at that image, but from looking at it, it looks like it's actually worse than the one in 2017. I would say 2017 is a better image than this one if you're talking about reconstructing the ring structure, because this one you would interpret as a central peak. You would never guess that that it comes from a ring.
Maybe as we are close to the end actually of the coffee break even, Shep has a question.
Yeah, thanks. A very quick question. It's a very nice talk. It seems to me that you'd be able to differentiate between the photon ring and the jet base rings because of time variability. So could you not observe this for a full year, let's say every week, and expect to see dramatically different time behavior for the jet base rings versus the photon ring?
That is very good question. And we have not yet calculated the time variability, but we expect that the direct images will show more strong time variability, and the photon rings show less time variability because it is formed by the complicated trajectory of photons, and the time different variation will be smoothed out compared with the direct emission of the stagnation surface. And maybe the time variability is maybe about light crossing time of the position of this ring, and so it will maybe one day, might be less than 1 day or so. This is my expectation for the time variability.
Thank you, Tomohisa. Are there other points to raise? Or should we close the parallel session?
Thank you very much.
Okay, so if there are no more questions, thank you very much, Tomohisa. Thank you to all the speakers, and I think we can go back to the plenary session. Thank you very much to all.